Okay, so today I'm going to try and give you a crash course on Python. And I know like 161 is where our Python course is taught, but if you need a refresher or if you somehow don't have a lot of Python, I'm going to try and give you the Python subset that you need to understand the code. So the guest book code that's there is only like, I would say 100, maybe not even 100. Not including the HTML, it may be like 30 lines of Python code. But there's a lot of stuff in that 30 lines that maybe isn't being taught in the beginning class. So this is more of an advanced Python thing to get your head around the code that is actually in the repo. Because what I want you to be able to do is after this class, go into that repository and start getting familiar with that app. Because really the next 2 weeks, there's very little lab work. It should almost all be you focusing on your homework assignment, like building your app. So there's like one web dev lab and there's a couple database labs, but for the most part, you should be working on your programs. So why did I choose Python for this class? Well, we have a full stack course, and the full stack course is doing Node.js. The reason why I like Python is that it's concise and expressive. It also has the ability to support multiple programming paradigms. So if you like imperative programming like C, you can do that in Python. If you like object-oriented like C++, you could do that in Python. If you like functional programming like Haskell, you can do that kind of programming in Python. This is both a positive and a negative. So and I mentioned this earlier with Go, that language, they were like, no, we don't want 3 different paradigms. We want one paradigm. And initially, Python, there was a Pythonic way of doing things, and that was before a whole bunch of other sort of programming language styles got rolled into Python. So now there's a bunch of different ways you can implement things in Python. Okay, it is a rare language that's used by beginners all the way up to experts. This is what a lot of people are recommending that we start teaching at the beginning just because of the ease of onboarding someone on Python. There isn't a lot of heavy-duty syntax in this language. And so the other reason why you would want to learn Python is that there's glue. So it's a glue language that has bindings for all kinds of code. So you'll see this all over data science and machine learning. You'll see this all over security. So if you take any security courses with me, stuff like Anger is a symbolic execution framework for the malware class. For the blockchain class, Manticore's symbolic execution framework is done with Python bindings. Debuggers have Python bindings now for you to control them. So it's all over security. And it is used somewhat for web development, not a lot, but there are places that do use Python as a web framework, a web development framework. Another key thing is that all of the Google Cloud services have API bindings that support Python. So any kind of cloud service that Google has, if you go to the documentation, there's language SDKs, and there's always one for Python. And when you do your first couple of Google Cloud Labs, you're going to be cloning the Python samples repo, and you can just see this massive library of examples of Python being used to do this, that, or the other on the cloud. So that is very helpful. This is an article from earlier this year, Netflix admitting that it's using Python everywhere. So security tools, recommendation algorithms, even a lot of the control for their CDN is written in Python. One of the things that you have to, we mentioned this earlier, is that it has this global interpreter lock. It doesn't like running multiple parallel threads. So you don't necessarily want to do the full-on HPC computation in your Python code. Okay, so this class assumes that you have some knowledge of the syntax. And if you do not have any Python, this slide deck contains a complete language sort of example reference for you. I am going to skip a whole bunch of the slides in this slideshow because it's all the basic stuff. But if you really want to go back and understand those things, then just go through the entire set. And preferably do it with a Python interpreter because there's a lot of code examples. When you type those into the interpreter, then you'll be able to understand more of the language that way when you can see the results of Python commands. I am going to cover a targeted subset. So these are the things I'm going to cover, and these are the things that appear in your in the guestbook app in the repository. So these types of constructs, if you haven't had them in an initial Python course, they might be really confusing. So I want to present those to you today. So let's start out with some of the basics, numbers, strings, and variables. So just so that we all start at the same page, with Python, everything is an object. And every object you can think of as a box. And it's a box that has a particular value and a particular type associated with it. There is this class keyword that specifies the definition of the object. And this is basically the mold that makes that box. So what is the framework that objects of that class are made out of? So there are some built-in data types in Python. So built-in box molds. Those are booleans, integers, floats, and strings. So these are some examples of them, of each kind. There is a built-in type method, and when you use it in your program, you can get the data type associated with whatever the object is that you're looking for. Typically, it's a variable, but if you do a type and it's a string, it'll give you an str object, a float, an int, and a bool. Those are the basic data types in Python. Python variables name the object, and the abstraction is like putting a post-it note on the object that you want to name. So when you do an assignment statement in Python, you're basically attaching a name to an object. And it doesn't actually copy a value. And this is important because this is the abstraction. When I say a is equal to 7, there is some object in memory labeled 7, or that contains 7, and then a is equal to 7 just puts the a post-it note on that object. And then when I do b is equal to a, what I'm doing is that I'm attaching a post-it note b onto the same object that a is posted onto. So this is like taking another post-it note and sticking b on top of it. So that when I set a to 8, what I'm doing is I'm taking the post-it note off of 7, putting it on 8, so that when I do a print b, it stays at 7. So you're not passing a reference. This is a value that you're pasting the post-it note on. Okay? That's a key point of confusion sometimes in languages. Okay, from these basic data types, we'll be combining them into more complex or compound data types. And these are the tuples, lists, dictionaries, and sets. Python tuples are immutable ordered sequences of objects. And these are used to pass parameters into functions. So if I have a function and I want to pass it a list, or a tuple of arguments, I'll use this notation, the parentheses notation, to send that in. So in this case, I have foo as a tuple, and it's got these 3 items in it, integer, float, and a string. So the objects are separated with a comma, and you can index a tuple using array indexing. So the 0th element, foo of 0, gives you 1, and then the type of 1 is an int. Likewise, foo of 1 and foo of 2 are floats and strings. Okay, so you use the square bracket operator to index into a tuple. It's immutable, so if I try and change foo of 2 to a different string, this will give me a type error, because the tuple is supposed to be read-only. You're not supposed to write the tuple. Okay. If you want to define a tuple with a single element, you have to use a comma. You have to use this notation in the bottom. So here, if I do a foo and I put parentheses 1, this is going to get reduced to a single integer. So if you want a single element tuple, then the notation is parentheses 1 comma, and then you leave the rest blank. So this can be confusing when you see this notation going around in source code. That is why they do this, because parentheses 1 would obviously would reduce to a single integer, but this will be a tuple. Okay. Python lists are mutable ordered sequences of objects. So the only difference between a tuple and a list is that one is mutable and one is immutable. So for this, they're denoted with the square brackets and then separated with comma. So I can create an empty list with the square brackets above. I can create a word list, a list of words separated by a comma. Lists can also have mixed data types as well for that mixed list below. And then as with a tuple, you can index these things with the square bracket operator. So the types of each one of these is string, int, float, and bool. With lists, you can do something called slicing. So this is a notation that's a good shorthand for accessing Python lists. So in this case, in the square brackets, there is this notation where you have several integers separated by colons. And the first parameter is the start index. Where in the list do you want to start? The end is the last element that you want to end at. And then the step size is what is the interval that I want to access this list. So if I have a word list with these 4 words, and then I say I want the first element to the end, so getting rid of the 0th element, then I can just do 1 colon, and then it just gives me the quick brown fox. If the colon is missing, so there's 2 colons here, if the colon is missing, then it just assumes that it's the first 2 that you're trying to specify. I can also do word list colon 2, and then this will get everything up until the second element, non-inclusive, so this is the 0 and the first element as a result of this slice. And then if I do a double colon 2, this means I want every other word in the list. So then it's the 0th and the second element that I get returned. So this is common slice notation for Python lists. One of the other things you can do with this step size is that you can reverse a list using this -1. So this says rather than going in increasing order, I'm going to go in decreasing order, and this just gives you this list reversed. Okay, you can test for whether or not a list contains a particular item using the in keyword. So the in keyword is used for other operations where you're trying to test membership. But in this case, for lists, if I want to see if the object foo is in word list, then foo in word list will return true or false. And of course, that word isn't in this list, so this should return false. Then if I do the in word list, this Boolean is true because the 0th word is the. One of the things with lists is whether or not, with lists, sometimes you'll want to sort these things. There are 2 different ways to sort a list. One way is to sort the list in place. This means you're actually modifying the list data directly. So that's what the sort command does. If I do a word list dot sort, which is the second line, then when I type word list again, I get them sorted in alphabetical order. And then the order is ascending order unless you supply this sort function with a keyword reverse to say, I want the reverse order. So keyword arguments are something that not all programming languages have. These are special, it's like you supply a dictionary to the function call and say, if certain keys are in there and they're set a certain way, then you can change the way the function operates. Keyword arguments are something we're going to get to later in this lecture. If you don't want to sort the thing in place, then this sorted, built-in sorted function will allow you to create a new list with the items of word list sorted for you. So if you want to keep the copy of the original word list, then you can set a new object to the sorted version of this word list, and this will create a copy. It'll create another copy and then sort that and then return it. Okay, copying lists, if you remember, the variables are post-it notes. So if you do word list is equal to the quick brown fox, and then you set this foo list to that word list, it's just going to put another post-it note on that object. So that when I change foo list of 0, foo to foo, I am going to get this. This change in word list. Because they're both stuck on the same object, even though I have a different reference to this, the first element is going to change. Okay? If you want a separate copy and you want to change that separate copy and then keep the original the same, then you have to explicitly make a copy. So that is what the copy method is going to do. So in this case, I have foo list is wordlist.copy. It creates a second copy of this thing so that when I change foo list, then word list stays the same. So this is where the post-it note abstraction really matters. When you start doing this kind of things, you really need to get this straight in your head. What is Python actually doing with these assignment statements? Okay, the next data type is the Python dictionary. This is a mutable associative array of key value pairs, just like a dictionary would be with words to their definitions. So the keys have to be unique. They also are immutable, the keys themselves. The values that they point to can change, but the keys themselves are immutable. You can't change a key after you've already inserted it into the dictionary. The keys themselves can be any of the basic data types, so a Boolean, an integer, a float, tuple, or a string. And it's denoted by the curly braces with commas separating individual key value pairs. And this is really common to store JSON. So JSON it stands for JavaScript Object Notation. This is the data format that's typically passed back and forth between web clients and web servers. It's just a natural syntax to then put into a Python dictionary because JavaScript is a whole bunch of key value stores, or JSON is a bunch of key value stores. Okay, so here's an example of a dictionary. So this is the dictionary bar. It's got two key value pairs. The first key value pair is the key 1 and the value 2. The second one is the key string of 3, and the value is the float 4.0. You can test for membership with the in command, and the membership test is for the key. So you can check to see if your dictionary has a particular key using the in keyword. So in this case, is there a 3 key in bar? Well, yes, there is. Is there a 5 key in bar? Well, no, there isn't. So that's an example of using in. You can get a value by using the square brackets with the key. So bar of 1, because that key exists, will return 2. And then bar of 5, because that key doesn't exist, will give you a key error. So that'll throw a Python exception. You can get all of the keys from a dictionary by doing bar.keys, and then the data type that you get back is a dictionary of keys that has 1 and 3 as part of it. If you want to turn this into a list, then you would have to actually pass that into a list function. You can get all the values in your dictionary by doing a .values on it. So bar.values will return a dictionary of just the values. So in this case, 2 and 4.0. You can get all of the key value pairs as a list of tuples doing the .items. So when I do bar.items, then here is the first tuple, 1, 2, which is that first key. And then the second tuple is 3, 4.0. And that's returned as a list. So anytime you are looking, this is especially the case when you're doing Python in Google Cloud and navigating the API documentation, you have to really know what kind of types are being passed back and then how your client needs to handle them. So, for example, bar.items, you have to go and you have to look, well, what is this thing returning? It's returning a list of tuples, and then I know the data format so that I can subsequently access it. Similarly, for .values, you have to know that this is returning a dictionary. Like, it's not returning a list. It used to return a list, but then they changed what it returned in Python 3. Like in Python 2, it returned a list. Python 3, it's returning a dictionary. You have to be savvy enough as a developer to be able to go check the documentation on the data type that's coming back from every single API call so that you understand, so when you're getting type errors, you can understand why. So that's an issue with developing with Python on the cloud. Okay. The next part is control flow and comprehensions. So with Python, white space matters. So the code blocks you'll find are delineated by their indentation level, and it's usually spaces. Generally, if you have a line that wraps around and you want to escape out the new line, it's done with a backslash. So this expression 1 + 2 + 3 is going to give you 6, even though it wraps around the line. You can split out parameters without the backslash. So this is often done for readability. You don't want a function call that wraps around lines. So what you can do is in between the parameter declarations, so here is a named parameter, after the comma, you can just stick a character return. And this is what I would recommend to align your function call so it's much more readable. Python has the traditional conditionals, so if then else. It does if, else, and then else if. And these statements, these conditional statements will all end with a colon, but no parentheses are required on the condition itself, unlike C. So here's an example. If n mod 4 is equal to 0 is the conditional, print divisible by 4. And then you would have else if, and you can check if it's divisible by 3, divisible by 2, and then finally the last else for the final clause. Okay, equality in Python. So we talked about how JavaScript really messed up their equality by doing type coercion. So Python, because it's strongly typed, did not mess it up. The double equals and the is are the two ways to check equality. The is checks to see if the objects are the same. If both post-it notes are on the same object is basically what is doing. So this is called shallow or referential equality. So the post-it notes are attached to the same box. The double equals is going to check to see if the bit patterns stored inside the object are the same. So this is called deep or structural equality. Intuitively, it's A is equal to B. And for any type, if you have referential equality, you automatically have structural equality, right? The thing is equal to itself. But if you do something like copy a list, so we said earlier, I can make a copy of a list. Now I have two lists that have different references, but they're structurally equal. So in this case, structural equality doesn't imply referential equality. Sometimes you need one, and sometimes you would need the other. But you can use double equals, and there is no, as far as I know, no triple equals in Python. Okay, so there is no coercion that would require you to have another kind of equals. Okay, the next conditional is a loop. You would typically see a for, but sometimes you'll see a while loop. So here's an example of a for loop. So for some variable in some iterable. In this case, your iterable is a list, but Python has this whole set of classes called iterables that you can use to drive loop invocations. And we'll talk about what iterables, what kind of iterables are out there later. One kind of iterable is this range generator. So this function will generate values one at a time when you ask for them. And Just like the array notation, you can tell the range operation to have a start, a stop, and a step. So in this case, if I say range going from 0 to 3, it'll pass back to this for loop, if I use it in a for loop, 0 and then 1 and then 2. If I do 3 to -1, so this is my start, this is my stop, and I want to go in reverse order, then this will give me back 3, 2, 1, and 0 as part of my output. Okay, so when used with loops, you can use this generator function as an iterable, and for n in range 1 to 5, you'll just print 1, 2, 3, 4. And it will pull out of this generator function one piece of data at a time, similar to this list. So a list is an iterable that can return its values one at a time as well. Okay, so this is equivalent to a C-style loop using a while, where you would set an index. So this particular one is similar to this loop, so setting an initial I is equal to 1 and then doing this loop. The biggest difference here is that here you've said this is exactly the range that I want you to execute this loop in. For here, this is actually not known. This condition on the underlying processor, the processor is doing this comparison every loop, and then it doesn't actually know the number of iterations. So if you remember CS430, this may have been a long time for you, this branch prediction problem makes this much slower than actually knowing the number of times you want to execute something. This can be done with a single register, account register. Say, I want to do this 5 times, whereas this is actually a conditional that's going to have much lower performance. Okay, this leads us to comprehensions, which are something that, unless you've taken the functional programming class, you probably haven't seen a lot of. So in order for me to explain what a comprehension is, I have to go through some definitions. The first definition is the iterable object, which we were just using in the previous slide. An iterable is any compound object capable of returning its members one at a time. Okay, so there is this special next method that will pop off the next value in that iterable. So when you define a list, the native list class supports this next method. Same thing with that generator function that you saw earlier. So range, this generator function supports this method that will simply return the next value off of it. The next thing is an expression. An expression is a piece of syntax that can be evaluated to a concrete value. So here are some expressions: the sum of 4 plus log of 8, the integer 7, the string concatenation hello and world, and then x plus y, where both x and y are known and can be assigned so that you can calculate the result of that sum. So basically all functions that don't have side effects are considered expressions. And then the last definition is a composite or compound data type. These are data types that are built from the primitive data types. So the ones that we just covered, tuples, lists, and dictionaries and sets, those are examples of compound data types. Okay, so this is all to get to a comprehension, and this is something that is used in the guest book. So a comprehension is a combination of an expression, an iterable, and potentially a conditional that returns a new compound or composite data type. And so the idea here is it's going to apply an expression to each item in the iterable and then return a result. Okay. So the idea of a comprehension is to, instead of bringing data to the code in a for loop, so in this case, I have this for loop, and then the data is processed here in place. Rather than bringing the data to the for loop, I can then do something like this, where I bring the code of the for loop to the data itself. So I have an array, it's a list, 1, 2, 3, 4, and I create this list comprehension that says, create me a new list, and the new list has the items x plus 1 for all x in array. And what this is going to do, it's going to do the exact same thing. It's going to increment each element in that array and then return you a copy that has array is equal to 2, 3, 4, and 5. Now, let's see. So in this case, x plus 1 is your expression, which is over here. So it's a combination of the expression. The iterable is this list. And the 4x in array is going to give you this iterable that's going to go through this array one at a time. Okay? And then the list comprehension of x plus 1 and that list will then map the x plus 1 operation over each item in that list, giving you 2, 3, 4, and 5. Okay? And this typically, a lot of people prefer this kind of syntax over the more imperative structure. Are there questions about list comprehensions? I've shown you a list comprehension, but there are dictionary comprehensions, there are set comprehensions, there are all sorts of comprehensions. This is the sort of the Pythonic way of doing functional programming. Python has maps and filters and reduce operations, but I think those are being de-emphasized for more of these comprehensions. Okay. One of the things, the reason why I'm bringing some of this up is that you're going to see this kind of pattern where you're taking the function and you're bringing it to the data. When we talk about data processing pipelines and sort of what's happening with data science, you don't necessarily want to bring the data in, compute on it, and then store it back out. You want to treat things as function transforms, where the data is getting passed between functions to functions. You're deploying functions towards where the data is, and then you're doing the processing in this style over here versus something that looks like this. So it's just a preview for the very last week of this class. Yeah.
So does it actually like save you some time or like some like running time that you're not having to, like, do you have to end up having to like move numbers less around?
Good question. The answer is if you want to go to this. So when would you use one versus the other? If it's a performance reason, there are different reasons why you would use an imperative loop versus a comprehension, and then this talks about it. Different situations where one might be usable over the other.
For example, like like systems where like you want a for loop that's going to optimize to like unroll the loop or something, right? Like some interpreters can do that, right? Could that not do that for like a list comprehension?
I don't want to give you a very simple answer for something that's probably got a lot more moving knobs than I even know. But what you can do is you can time these operations just to see what kind of overhead am I undertaking for creating another copy of this versus doing things in place, but then maybe doing things in an inefficient way in place. Because this does make a new copy, right? Like this comprehension is a new list that you then assign to an array. So if I would assign this to something else, then you would have two versions of the same array. This can only do in place, right? I can only make an in place modification using the loop. Okay. But yeah, I put that link in there in case you're really interested. I mean, the speed up, the differences are marginal. And you're not using Python for massive loops and enormous amounts of data, so maybe it doesn't matter. Maybe it's more of a programming preference, a readability issue versus a performance one that you would want to consider when using one or the other. Personally, I program more to the left, but I know all of the faculty, all the programming language faculty are like, no, go to the right. go to the right. Yeah. Okay, so here are some examples of list comprehensions, and I'm only doing list comprehensions because the only comprehension that's in the code is a list comprehension. So here's the format of a list comprehension. It's the expression for item and iterable. So in this case, ns for n in range 1 through 6. This gives you the list 1 through 5. Okay. I can do a comprehension that's this, where it's word is an array of, I mean, it's a string, but then for each character in this string, I can take the ord of the character, which is the ASCII key code of that character, and this would print me a list of the ASCII key codes in decimal for that character. I could also do something like this, where I can say for every character in this word, I'll take its ord, I'll subtract hex 20, and then I'll reconvert that into a character. So this basically capitalizes the letters, if you remember ASCII. I can add a condition to it. So I mentioned that there is a condition that you can attach. So expression for item and iterable, if this condition holds. So n for n in range 1 through 6, as I had before, but only the ones where n mod 2 is 0. And then when I type ns, I'll just get the even numbers. Okay. So that is that's a list comprehension. Are there questions about that? All right. The next thing are functions. Python has multiple ways for you to call functions. The first way is the traditional way that you're familiar with any kind of C-like programming language, and that's with positional arguments. And these are bound to the parameters based on the position in the function call that they have been given. So if I have this function, this power function that takes a base to the power of n, then if I call it with power 2 of 3, then the order of the arguments determines this is 2 cubed and this is 3 squared. So just as you've seen before, Python allows you these keyword arguments, which allow you to pass a dictionary specifying what the key B and the key N actually are. So in this case, I can say power B is equal to 2, N equal to 3, and I can also reverse them. So N is equal to 3, B is equal to 2. These two things, even though they're in different orders, this will generate the same dictionary, and this will give you the result 8. Okay, so whenever you see KW args in Python, this is a dictionary specifying your arguments as a keyword dictionary rather than as a positional argument. So those are that's something that's unique to Python. Okay, another thing I wanted to cover is docstrings. So a docstring is a string at the beginning of a function's body that can be pulled out as documentation. And almost every programming language has some kind of docstring standard. And the reason why they've done this is so that the code can self-document. Because before, what you would do is you would document the code inside of the code, and then you would create another web page for the SDK documentation. And they're like, all that stuff is replicated, and moreover, the website stuff gets out of date, right? Like if a developer changes something in the code, like that website might not get updated to reflect that. So you want the thing to be, you have one definitive place to do the documentation, and it should be in the source code. And then what you would do is then generate those docs from source code. So in this case, I have the power function, and I also allow this function to take in a keyword argument pp, which means pretty print. So with the documentation for this function calls says, you know, if I set this param pp to true, then I'll pretty print b to the power of n, which will actually give me a whole string format that gives me the result. So then, when someone imports your code, so say I import this as part of a package, and then I need some help. I'm like, I don't know how to use your function. Then I can just type help on power, and then it will return automatically the documentation, right? It'll say how this thing is used. I didn't put an extensive amount of documentation here, but it should actually tell you what the data types of all the parameters should be, what the data type of the return value should be, the exceptions that the function can throw. All of those would be put in fact, I have an example on the next slide that shows this. All of that would be put in the documentation, and I apologize for the contrast. This is really hard to read. So in this, there's the very beginning specifies the description. So this piece of code connects to a particular URL. And then it connects to that URL and it supplies it with a username and password. So this was effectively used to connect up to that Natus CTF, if you remember the basic auth thing. So it's supplying a username and a password to that basic auth protected page. And this person has documented all of the parameters, the 3 parameters, and it says, yeah, this is the username, the password, the URL. They should all be specified as strings. And then the return is the response object of the connected URL, and then this raises an HTTP error when the connection can't be made, and then this is the code that actually implements going to that URL, retrieving the page using a username and password, and then returning the content, the response object as the final value. Now, typically, this isn't exactly what you want a little bit more that specifies the data types. So if I am this says, well, this actually specifies the data type. It says a response object, but these things should say strings, just in case it's not obvious what the data type actually is. So I cover this because when you are programming your homework, we want to see this, because it's good software engineering practice for you to include this as you're programming your code. So you'll see in the rubric for the homework that PyDoc strings are required and graded, and this is what we're looking for your code. Okay, one of the things with Python is that it is you can program it functionally, so it's got the functional language support. Functions are first-class objects in Python, so you could do something like this where you have a function run something that can take in a function as a parameter and then do something like this, execute the function. So that when I have 2 of these functions defined, answer and hi, I can then send one of those, I can send them to this run something function, and then it will execute it directly. So you're passing functions as objects, and that's the facility for doing so. And I cover this to get to nested functions and decorators. So a nested function, you can think of nested functions as a local function variable. It is a function that is scoped to the object that it's defined in, and only then, that object. So this is different than C. In C, when you define a function, it has a naming scope that goes across the file, and in fact across multiple files if you've linked them all together. In Python, you can define a function that only has scope within another function. So that's a nested function. In this case, I have an outer function, and within it, I define an inner function whose name is not scoped anywhere outside of this function call. So in this case, I have a modulus 3, and then I define this inner function to be a times 2 mod, a modulus, and then I return the result of inner with a as the parameter, and then it does the modulus, mod 3. It multiplies by 2 and takes the modulus. So when I do an outer of 5, it will return 1, but then when I do an inner of 2, it says, I don't know what that function is. Now the reason why you would do this, and you'll see this in different places in Python code, the reason you would do this is to get rid of the namespace pollution. So if you know that the only place this function should be called is within the context of an outer function, then you can free up the name. Say inner is a very popular function name. Well, then this inner specifies the one that's just to be used within that call. Okay, this gets me to decorators. So a decorator is a function that takes one function as an input, and then it returns a wrapped version of it. And the wrapped version is basically implemented as a nested call. So here I have a function called documented, and this document call takes this function as a first class object and defines a inner function called new function. And as part of this new function, all that the new function does is that it prints the name of the function, the positional arguments that it might have been sent, the keyword arguments, and then it calls the function that it was passed. So all this thing is doing is printing out the documentation, or printing out what is, it's like a verbose function call execution where it's telling you everything that it's doing, and then it will actually, on the inner, it will return, it'll call the original function and return the result, just like you would normally. And then what I'm going to do is I'm going to return this as a new function, right? And so this thing, when I call documented, I'm going to say I want a new function, and that new function has all this stuff wrapped around my original function call. So that's what this piece of code is doing. So I can have an original function that just adds two integers, a plus b, and then I can create this decorated add integers that says I want this function, decorated add ints, to be the result of calling document it on the original function and returning that. And this decorated add ints will now be this function that got returned, that prints all this stuff out before it actually does the inner function. So then when you invoke this decorated add integers with 3 and 5, you get something that looks like this. It'll actually go and print these messages out, and then because you called it with positional arguments, it'll spit out the positional arguments. If you invoked it like this with a dictionary, with keyword arguments, so in this case, a is equal to 5, b is equal to 2, that says I'm going to pass my function parameters as a dictionary. Then what you would get is this as an output, where it's the positional arguments are null, and then I have the keyword arguments is this dictionary that I sent as part of that call. So is that probably they don't teach that in 161, I would imagine. Okay. The thing is for advanced Python, you will see this quite a bit. And in fact, a lot of because there are so many parameters in some of these Python calls in the cloud, you're specifying so many things, it has to be done as a dictionary. Because you can't specify every single parameter, or you don't want to specify every single parameter available on a particular function call. So what you'll do is that the list of parameters, there might be 20 parameters, they'll all have defaults, and then you specify the dictionary of the things that you don't want defaulted, that you want to be your own thing, and that's done this way with keyword arguments. Okay. Any questions about the mechanics of what Python is doing?
So like A and B, those will be changed, and then just everything else is left alone.
Yeah, so if I had pretty print on there, it would just be the default. And typically when you are defining functions, you would define a default value for any of these keyword arguments. Like on this one, I specified a default. The default here is specified in the function declaration, so default this value to true. And it's only if I pass a keyword argument that says it's false will it go the other way. So this is something you'll see, is that these things might be required parameters that if you don't set will throw an error. And then these might be things that have defaults, but you can optionally set to a specific value.
So your keyword dictionary should always include the ones that are required.
Yeah, the ones that are required, and then any other ones that you might want to override. That's the convention that I've seen, at least, with Python being used. Okay. Do other languages do that? I'm not super familiar with other languages. I don't know that they do. Like JavaScript does. As far as I know, JavaScript doesn't do that kind of stuff. They're strictly positional.
Yeah, it was bugging me this summer because I was like, wait, this is better in JavaScript. Why can't you do that in Python? This is the solution.
Oh, so there is. Okay, so JavaScript does have the similar construct. Java. Okay. All right. But it might be coming to a Java near you, or no, a JavaScript near you. Yeah, because they're changing that thing. That's why I ask, because like I'm not sure what ECMA 6, 7, 8, whatever they're on. Because all these languages are competing against each other for usage. So they'll see something really cool in one language, and they'll be like, okay, we need that, and then they'll actually implement it in the next language. Any other questions about this? Okay, decorators can have special syntax. This is a pattern that's so common that they decided to use this @ symbol. And this can be used when a function is defined where you only want the decorated version. So in this case, you remember I defined the document it decorator. I can just invoke that with @documentit and then define my original function. And what this does is that it just gives me the decorated version. So when I put this right in front of the function definition for addints, then what I'm going to get is that addints is only going to be the decorated version. So this is what you'll get when you do an addints 3 of 5. You'll get the decorated version that has the positional arguments 3 and 5 and gives you 8. Okay. So all of that is going to be useful here in a second. So there's common places where you would want this. Like, why would I want to attach this kind of code to to this function? Why don't I just implement it in the function itself? So the reason is that there's a lot of cases where you always want to execute the exact same code for a whole bunch of functions in your program. And that's when you would use a decorator. You want to keep that code in one place so you're not re-implementing it in every single function, right? Like say it's performance code, and I want to time the code, the execution time of every piece of code. I could copy and paste that code everywhere, or I can use a decorator and then just decorate all my function calls with that performance code. So anytime you have operations that you really want to run on every invocation of a function, you can modularize that with a decorator. So repeated setup and teardown procedures, timing, which I mentioned earlier, checking the argument types, like making sure that you do some input validation on the function call. That could be done using a decorator across all your function calls rather than re-implementing that everywhere. And then concurrency management. If I have a critical section, a piece of code that needs to acquire a lock, I can use a decorator to acquire that lock every single time and release it upon exit. So you can put that all in this decorated piece of code. For us, for a web developer, you might need a decorator for ensuring authenticated access, right? Like I have to make sure that this particular route can only be executed if you're logged in. And then anyone else who's directly trying to access that route without being authenticated gets kicked out automatically. So this is a YouTube on a Python app that uses this @login required decorator to make sure that particular paths of the web app are always only accessible to authenticated users. And the other place, the reason why all of this, I'm going through all of this is that the Python Flask route definitions are done with a decorator. So this is how the Flask package is binding routes to particular code that will process that route. Is done with the decorator. Okay. And I'll get to how Flask uses it in the next lecture. Okay. Chapter 5 deals with modules, packages, and programs. And I'm also going to include the tools here because Python needs some tools to manage all of the packages that you have installed. So the first thing is that there's way more than 39,000 now. This was from a couple years ago. The PyPy repository is where all of the user-contributed packages reside. And so there's over 40,000 of these things that are out there that you can include in your Python program. And so in order to access and install all of that, Python comes with this pip package manager. So pip installs packages is the name of that. It's a recursive acronym. And this is equivalent, if you're familiar with JavaScript, this is equivalent to the Node package manager in JavaScript. And it's really easy to use. You just pip install the package name that you're interested in, and then you can then import it. So here's an example for requests. It's a package to do HTTP and URLs. So you can install requests using pip install requests. And then after you've done the installation, then in your Python program, you can import the requests and then do a request.get whatever URL you like, and then it will print the output. Okay. One of the biggest issues with this is that it requires administrator access to be able to install things in the system Python directory. So typically Python is installed in user bin, and then all of its packages are in user lib. And cat is not going to let you install anything on user lib or user bin. So if you log into Linux Lab and you want to get your Python environment, you're not going to be able to do that on the system Python. To get around that, Python has this tool called virtualenv, and there are similar other tools that provide the same functionality. But the idea of virtualenv is to create a local installation of Python in that home directory. So npm does this automatically. When you do an npm install, it only installs in the local directory that you're running the package manager in. Virtualenv allows you to get the same thing with Python. So you establish a virtual environment and you specify a directory to put that environment in. So in this case, I'll cd into the directory I want to run my app from, and then I'll create this directory env, and I'll say virtualenv. Actually, I don't have to create this. It'll get created automatically. I say virtual environment. I want a Python 3 environment because there's multiple versions of Python. You should always use Python 3 for this class because I think Python 2 goes away at the end of 2020. So virtualenv Python 3, and then specify the name of the directory that you want to install it in. And what this is going to do is it's going to go and it's going to copy an entire Python 3 environment, a vanilla Python 3 environment, and it's going to copy it into that directory env. And then what you do is you activate this environment. You say, you know what, I don't want the system Python anymore. I want to activate this local environment, so I'll just do a source of env bin activate. And this sets up your shell so that the Python that you are then using is the Python in env bin rather than the system Python. Yes?
Is virtualenv, so is that actually downloading Python for you and then creating the environment, or is that
It's copy. It assumes that you have Python 3 installed. So if you do this, and actually I think when you apt install virtualenv, it'll make sure you have all the Python installed. It'll install Python 3 automatically when you install this. So yeah, but it does assume that you have a working Python 3 installation on your machine because it's just going to copy those files into that directory env. And within this env directory, there will be a lib directory so that when you do a pip install, request, it's going to actually download the package and install it in env lib. The actual Python code for implementing requests will end up in this directory. And you can go and you can actually, if you don't like the version of Python requests that is there, you can actually go and edit that package if you'd like. Because all that code is in a library, is in the lib directory. Yes.
And if you didn't, would it install itself globally, right?
Yeah, we'll try to. So yes, it is important before you do any of your pip installs. If you are intending to install it in your virtual environment, you must do this first. Otherwise, pip install will try to install on the system directory. The convention in Python is because you don't want to have a user download your app and then have the user do a bunch of pip installs. The convention for Python is that in any Python project, there's this requirements.txt file that you would specify all of the pip packages that you need installed and their versions. So sometimes these packages get updated and they're updated in a way that's incompatible. So if you need a specific version of a particular package, you can actually specify version numbers in requirements.txt, which we'll get to later. But pip install -r requirements.txt. Requirements.txt is just a list of packages, one package per line, and then pip will just install all of them, all in one shot. And you'll see in the repository for the guest book, there's 2 lines. There's like lock file and Flask are the 2 packages that I require in the guest book app. And then a pip install -r requirements will just get those 2 and install it in the local environment. Okay. Questions about virtual env? You'll be doing this a lot in this class, as it turns out, for all of your development. Okay, so the one thing I don't want is a full-on Python interpreter every time I do a git clone of your homework. Or Leslie definitely doesn't want that either. So in Git, you can specify that the env directory is ignored as part of the revision control. So definitely name your environment env, and definitely put env in the git ignore so that when you go and you commit and you push your repo, that directory doesn't get pushed. Because we don't need to see that directory because we can regenerate that using the pip install requirements if we want. Okay. And I think we had this. I think that's probably in the instructions for homework 1 where we had you add that. Okay, so you do all that installation, and then later on, when you actually want to use this thing, you just cd into the directory that has your env folder, and then you just activate it. And then you can work as you'd like. At the end, when you're done working on your code and you're done running your stuff, you can either deactivate it or you can just exit the shell as part of your workflow. Okay, so you have a way to get packages in your program. There are multiple ways for importing code from packages into your program. The 2 keywords that you need to know are the from and the import keywords. And this is both keywords are used to get basically the library code into the namespace of your Python program. Okay, so there are 3 different options that we're going to go over. The first is to import a specific function into your Python program. So you have this package, and you know you only need 1 function out of it. So the way you can do this is you say from this package, XLRD, this is an Excel reader, is this package. From that package, import only a single symbol open workbook. And then I can import, so I'm importing that name into my namespace so that when I do a book is equal to open workbook, and then this is the Excel file, it knows to get it from XLRD. Okay? The other way to do this is to import the package name itself. So I'm just going to import the entire package. And then when I want to access any of the code inside of that package, I'll just type xlrd.openWorkbook. And then I can get the code executed that way. The last way is if I don't, so you'll see this a lot for something like TensorFlow. It's like, God, I don't want to write TensorFlow dot this, that, and the other on every single line of my machine learning code. You can do something like this. So if this is a function that you're going to call, or a package whose functions you're calling everywhere, you can say import XLRD as this name. And this imports all that code, imports this package using this name, and then you can call this as x.openWorkbook. So you'll see with TensorFlow, people always use import TensorFlow as TF, and then everywhere in their code is TF.this, that, and the other. Are there questions about importing? Okay. In this class, you're going to be making your own packages, and you're going to make packages from modules that you create yourself. So what are these things? A module is just a Python file. It's any file that's got Python code in it that contains either functions or classes. A package is a collection of modules in a single directory. So if you have a directory with a bunch of Python files in it, you can make that a package. And the way to make that a package is to create in that directory a special file called __init__.py. So this name, __init__, this is a special name in Python. It is used for the constructor of classes, and it's also used as like the constructor for packages. So if I want to import a package, the thing that gets called to initialize that package is in this file. When I want to create a new class, the thing that gets executed is a method called underscore underscore init underscore underscore. So that is how you create a package, and then the contents of that init file will get executed when you import the package into a program. Okay. One of the things with modules in a package is that they can obviously import each other, or they can import, packages can import other packages. Okay. So this gets us to the guestbook app. So the very first version is a simple monolithic guestbook app. The second version is where I split the model out. So you want your code to be modular, and you want to separate the concerns. So in the first implementation, it does MVC, but it's not organized in terms of packages. Like it's not, the source code isn't organized. So the second version of the guestbook app decides to take all the model code, put it in a separate directory. So GB model stands for guestbook model. And in the guestbook model, I have the underscore underscore init, and I have this capital M model. And the capital M model is my base class model. And then initPy has a function defined, let's say, that gets executed whenever I import this package. Then I'm going to import this from app.py. So app.py is in the directory, the same directory as the GB model directory. And then in app.py, when I say import GB model, it's going to go and include init.py and model.py into the namespace of GB model, so that when I then, in app.py, I say import GB model, it gets me all of this. And then from here, I can say, you know, I want model to be equal to gbModel.getModel, and it will know to pull this function out of init.py, execute it, and then return what getModel gives me. Okay. Likewise, I could do something like this from app.py. From GB model, I can import capital M model. And it knows, because you have put this GB model in its namespace, all the code in here is now visible after this from. So I can import that model as part of this call, and then I can invoke it directly. So this will instantiate the model from this particular file. And so now all of your model code is sitting here in this module, this package GB model. Okay, and this, I just wanted to show you this to give you an idea of how to modularize your app. If you end up growing the thing into a big sort of application, you'll want to separate these things out.
Just so you don't have to like import everything, right? Is that the reason for like dividing it like this, or is there
one of the reasons you want to isolate any changes. So if I create different models here, then I know I can isolate that in one area and then have a developer sort of work on that area. So it's just, yeah, it's an organizational thing, and it forces modularity, which is helpful. And this is such a tiny app that it might not make sense. Like, why is he doing all of this stuff? But it's a pattern. Like, being able to know that you can do this is actually very important. Like, if you did eventually need to split up your Python code, at least you've seen one way of splitting up your Python code.
this level of organization is more for the people who are maintaining the framework rather than the people who are using it?
Well, if you wanted to contribute your own package to the repository, you would have to build this as well, and that would go in into a package. But it's just so if you've seen how to make C modular with their libraries and how to make it so that you can split that thing up, this is a lot easier, I think, in my opinion. Okay. Objects and classes are the next thing I want to talk about. So if you recall, everything in Python is an object, and then every object is a box. And the class definition is basically the mold that makes the box, right? This is the recipe for building your boxes, is effectively what the class is. In Python, you can define a class this way. So the class keyword followed by the name of the class. And then, as I mentioned earlier, is the specially named function that is the constructor for this class. And then you can call it with parameters. So in this case, I have a person that has the name and the email as parameters. Implicitly, the first parameter in any of these calls is the self. This is similar to the this keyword in C++. It's a reference to a handle to yourself is basically what this is. And then I have a method that prints the two attributes, the name and the email from this class. And then an object is just an instantiation of this class. So I have Max, and I create a new person with that name and that email address. And then the base class person can be extended to create a new object type. So here is my base class person. It's got the init, it's got print contact. I can create a derived class, student, and in the definition, in parentheses, I have the class that it's derived from. So this specifies the base class for student, and the base class is person. So that's where it's going to inherit all of its default code. And one of the things that the student does is it adds a student ID to the person class. So because it's adding a third field, then it needs to overwrite or overload the init constructor, because this thing only initializes the 2. Now I have 3. So if I need to override this function, I have to basically declare it. Otherwise, it'll just use the default values. So if I don't touch print contact, then I'll have access to the superclass's print contact. So the other thing with student is that I might extend it to add a print ID call, which prints out the student ID. And then I can call it this way. I can create a student with these 3 parameters. I can call the base class's print contact without modification. And then I can do the print ID for the derived class. So that's just simple object-oriented programming in Python. Are there questions about that? Okay. I'm going to take a break, let's see, a 5-minute break, and then talk about Flask after.